Hello and welcome. Today, we're going to jump right into the engine room of Cisco's ACI multi-site architecture. We're talking about the Intersite network, or ISN. This is the critical Layer 3 plumbing that actually connects all your data centers together. Understanding how this thing works, well, it's absolutely key to building a multi-site fabric that's resilient, scalable, and most importantly, secure. So here's what we've got on tap. We're going to start with the basics, what the ISN actually is. Then we'll cover its non-negotiable requirements, things like MTU and OSPF. After that, we'll peel back the layers on the control plane, look at BGP peering models, and then see how it all comes together in the Nexus dashboard orchestrator. And of course, we'll wrap up by talking about how to secure the whole thing with CloudSec. Okay, let's dive right into this first section. Before we get lost in the weeds of configs and protocols, let's just make sure we've got a really solid handle on what the Intersite network is and what its job is in this whole picture.
At its heart, the ISN is the transport network that makes everything else work. Seriously, it can be pretty much any Layer 3 infrastructure as long as it supports just plain old IP routing. Its fundamental job is to provide the connectivity that lets your ACI spine switches in, say, New York, build VXLAN tunnels to your spines over in London. That's how we can stretch our fabric policies across huge geographical distances. Now, what's really interesting here is this mix of flexibility and some really strict rules. Your ISN can be super simple, like just a couple of routers, or it can be a complex global MPLS network. But how it plugs into your ACI fabric, that part is very specific. We're talking Layer 3 sub-interfaces on a fixed VLAN, VLAN 4. Now, here's a huge advantage. You don't need multicast support. Unlike ACI Multipod, Multisite uses something called head-end replication for all that broadcast and multicast traffic, which makes the underlying network design way simpler. Oh, and one last thing. Just remember you need the right gear. Only Nexus XEX platform spines or newer can handle the stuff at line rate.
Okay, so building on that, let's focus on the 3 absolute must-haves for any ISN deployment. If you miss one of these, it's just not going to work. Think of them as the non-negotiables. First up, and this one is a biggie, is the Maximum Transmission Unit, or MTU. Because we're wrapping our original frames in a VXLAN header and then another IP header, we're adding about 50 to 54 bytes of overhead. It's like putting a letter inside a bigger envelope. To stop that packet from getting chopped up and fragmented, which just destroys performance, the entire path through the ISN has to support these larger frames. So the standard recommendation is to set your MTU to at least 9100 bytes everywhere. And inside ACI itself, this is where you actually set it. You go into each APIC domain, right into the control plane MTU policy. Setting this is absolutely critical because it tells the BGP EVPN control plane, hey, it's okay to send those bigger packets now because we've made sure the network can handle it. Next up, routing. ACI Multisite absolutely requires that you use OSPF for the connection between your ACI spine switches and those first-hop ISN routers. It's how the spines learn how to get to the other sites, and just as important, it's how they advertise their own critical IP addresses into the ISN. Now here's the key takeaway, and you'll want to remember this. While that edge connection must be OSPF, the core of your ISN can run whatever you want. BGP, ISIS, EIGRP, it really doesn't matter. As long as you're doing mutual route redistribution between OSPF and whatever your internal protocol is, the reachability info will get where it needs to go. And this is awesome, right? It gives you a ton of flexibility to plug ACI multi-site into an existing wide area network. And finally, quality of service. By default, all that VXLAN traffic is going to get a DSCP value of 0 on its outer header. That means best effort. And in any real-world network, that's a problem. You really need to set up policies on the spines that map the internal ACI class of service values to the right DSCP markings for your ISN. The end-to-end process here is actually pretty slick. So a packet leaves Site 1, and the spine switch there takes a look at its internal cost value and slaps a corresponding DSCP value on that outer IP header. The ISN cloud then sees this marking and gives it the right priority. Then, when the packet gets to Site 2, the spine there sees the DSCP value and translates it back into the right internal cost policy. You get true end-to-end quality of service. It's really elegant. Okay. Now we're getting to the real nitty-gritty of how this all works under the hood. Let's break down the control plane and focus on the special addresses ACI uses to build out its connectivity and forward traffic between all the sites. First up is the BGP EVPN router ID. The easiest way to think about this is like a unique phone number or IP address for each individual spine switch that's connected to the ISN. This is the address they use to form those multi-protocol BGP sessions with the spines and other sites. It's really the foundation of the whole EVPN control plane. Next, we have the Overlay Unicast Tunnel Endpoint, or OUTEP. Think of this as a shared address, kind of like a shared mailbox, for all the spines within a single pod. So when a remote site needs to send unicast traffic to an endpoint in this pod, it just wraps it in VXLAN and sends it to this one shared OUTP address. And taking that same idea one step further, we have the Overlay Multicast TEP, or OMTEP. This is also a shared Anycast address, but this one is shared by all the spines across an entire site, not just one pod. Its job is to be the destination for all that broadcast, unknown unicast, and multicast traffic, what we call bum traffic, that gets sent over from other sites. So here's where it all clicks together. The spines in Site 1, they use OSPF to shout out their unique EVPN RIDs, and also their shared OUTEP and OMTPEP addresses, into the ISN. The ISN routers then pass these routes along over to Site 2. The spines in Site 2 learn these routes, and just like that, they know exactly how to reach the remote site for both unicast and multicast traffic. We know the spines establish these MPBGP peerings using their router IDs, but there are a couple of different ways you can design that. So let's explore the two main models you'll see: full mesh and route reflectors. Your choice really boils down to one question. Are your sites in the same BGP autonomous system, or are they in different ones? If they're in different AS numbers, you have to use external BGP, or eBGP. The big limitation here is that eBGP only supports a full mesh. That means every single spine has to peer directly with every single spine in all the other sites. Now, if your sites are in the same AS, you get to use internal BGP, or iBGP, which gives you the choice between that same full mesh or a much more scalable route reflector design. And this is where that route reflector model really shines. Instead of this crazy web of peerings, you just pick one or more spines in each site to act as route reflectors. Now, all the other spines only have to talk to the route reflectors. The reflectors then share all the routes between themselves. This hub-and-spoke model drastically cuts down on the number of BGP sessions, which simplifies your configuration and really improves scalability, especially if you have a lot of sites and a lot of spines. All right, enough theory. We've covered a lot of the what and why, so now let's get practical. Let's see how all these concepts, the TEPs, the RIDs, BGP pairing, are actually configured using the Central Management Platform, Cisco Nexus Dashboard Orchestrator, or NDO. And to make this concrete, we'll just use this simple two-site setup between San Francisco and New York. Now for Site 1, just notice the specific IP addresses we need to configure. We've got the OU tip for the pod, the OM tip for the whole site, and that unique EVPN RID for spine S1. What's so great here is how the NDO interface perfectly mirrors the architecture we've been talking about. It has this really clear hierarchical view. So at the site level, you configure site-wide stuff like the Overlay Multicast TEP. Then you drill down to the pod level to set up the Overlay Unicast TEP. And finally, you go right to the individual spine level to give it its own unique BGP EVPN router ID. It's a perfect, intuitive mapping from concept to config. So we've built the network, we've configured it, and traffic is flowing. But is it secure? I mean, in today's world, encrypting data wallets in transit isn't really an option, it's a requirement. So let's look at how we secure all that data flying across the ISN. You know, this is the million-dollar question for network architects, isn't it? Traditionally, securing your WAN links meant deploying dedicated encryption boxes. And that just adds complexity, cost, and one more thing to break. But what if you could do it natively, right inside the ACI fabric itself? Well, the answer is Cisco CloudSec. It's a super powerful, integrated solution that gives you strong line rate encryption for all the VXLAN traffic between your sites. The best way to think of it is like multi-hop MACsec. You see, unlike traditional MACsec, which is just point-to-point, CloudSec can secure traffic across any Layer 3 network, like our ISN, directly between the ACI spine switches. And honestly, the best part is just how simple it is. You're going to love this. In NDO, to enable end-to-end line rate encryption for every single packet going between your data centers, you just flip this one CloudSec encryption toggle at the site level. That's it. No extra boxes to manage, no complex crypto configs. It's powerful security made incredibly simple. So there you have it. We've walked through the whole life cycle of the ISN, right from its fundamental requirements and control plane mechanics, all the way to its simple configuration and powerful built-in security. The final question really is for you. Now that you see how this is all built, what new architectures for application mobility, for disaster recovery, and for workload distribution can you now go out and achieve?